music off now and we'll start. Okay. Alright, so this is just a probability exercises session, I guess you could call it. We could do some linear algebra too. I'm gonna try to work my way into being a little bit more open to, we could just work on whatever questions you guys throw at me, like on the spot, or, you know, I obviously, so I went through the resources, one of the first resource on probability in the resources section on Discord, and I took some problems from there to go over, but of course, like I said, I'm open to anything else. Also, I was discussing with Rex before the stream that I wanted to do like a 24-hour stream on Saturday, so I'll just be solving as many problems, I guess, as possible. We could focus on like linear algebra, probability, and any of the group theory stuff that I've talked about in any of the videos I made, but we can go into other stuff too, obviously. 24 hours is going to be a long time, so. How do I feel about spherical geometry? Like philosophically, how do I feel about it, or how do I feel about doing the problems? Or, it's a coordinate system. I'm not on Dr. Gold's schedule at 24 hours. What do you mean? Yeah, of course you can. Yeah, you can ask me questions about spherical geometry, sure. Yeah, if you want to ask me questions in the intersection of linear algebra, probability, like any sort of like quantum mechanics stuff, we could work through any type of stuff like that. I can't guarantee anything. There's obviously some math I don't know. A lot of math I don't know, of course. But I'll try my best, and we can work on it together. We can look up different stuff if I have no idea how to tackle it. So yeah, 24-hour stream. I just want to bring more awareness to like the whole math category here, because I didn't even really know it existed. I'm sure a lot of people don't, and maybe there's also a lot of people around the world that would tune in at like 2 in the morning that would normally see any of our streams. So I don't know, just get a little more followers and figure out the whole streaming thing a little bit more. Yeah. What are these questions? No, the Saturday coming up. So normally, well, not normally, but I just started doing streams on Saturday where I've been talking about a little bit of the research that I do. So I figured I'd just extend it for 24 hours. Cold Gold, where are you in Europe? Where is that in Europe? That would be like, what are you, in Russia? Oh, India. Is that India, really? Oh, yeah, I guess that could be, yeah. Oh, right, yeah, the half hour time zone, right? Yeah. So yeah, let's just start with I didn't really explicitly write them last time, so let's really focus on the expected value definitions. I just want to leave them up here. We're probably going to refer to them again. So remember, if I have a random variable that can take some finite number of values, and each one has some probability, and all the probabilities add up to 1, if I want to know what can I expect from like a single outcome, I'm going to be adding up this basically like this weighted sum over all possible outcomes. It's the value of whatever happens when that outcome occurs, and then the probability that it can occur, which is like P of I. So if you think it's like heads or tails, then there's only 2 options, and maybe if heads happens, some value occurs. Maybe the temperature is 100 degrees in whatever environment, and if you flip tails, it goes to some other value, like 50 degrees, something like that. Right, so this is the expected value, and the idea is like this is the average. This is like some sense the arithmetic average value that you expect per event in the long run. It's kind of like a mouthful. All right, but the example yesterday was like we had an example where I go to a chess tournament. I have a 10% chance of winning the tournament, and I win $100. Or I had a 90% chance of losing, and then I just won nothing. So we said that, you know, I either win $100 or zero, but in the long run, I'm gonna win about $10 on average per tournament because we took, because that was this expected value basically. And then we also said that if we played 50 tournaments, that this average would add up. So whatever the average was per tournament, which was $10, if I played 50 of them, then on average I would expect to win $500. So that's in the sense that's what the average is. In this sense, it's like an arithmetic average. So if the numbers are adding up, then this is what you could expect, per run or per like event, if you think of it like that. Right. Is this a good marker? Can we read this? I'm not sure if this is the best. I might switch to the black one. Okay, so then another quantity which I didn't really write last time, which is the variance. So this tells us, how much we expect to get on average. Then the variance is a measure of how distributed the possible values are. So you think in the extreme, if the variance is 0, then every possible value that I can pick is always the same. So there's only one xi basically. But the variance is a measure of how far we are away from this mean in the distribution. So this is going to be a sum. Again, we're going over the sample space, but then we take the xi's and we take their difference with this expected value. We square it and then we take, proportional to this probability, and we add all these up. So this is the expected value of x. The variance is how wide the distribution is. It's, in some sense, it's also an expected value. So this is the expected value of x squared minus the expected value of x squared. So it's kind of like the difference of it's the difference of an expected value and then the square of the mean. Simple average is also a nice term. So last time I was talking about the natural log. We had a similar situation where we had like a log of x on the inside and then log of the expected value where the log was on the outside. So do you guys remember Jensen's inequality we were talking about last time? What does Jensen's inequality say about these two values? So Jensen, just to remind you, Jensen was this statement about concavity and expected values. So if you apply a function to a random variable, depending on the concavity of that function, it can kind of like skew the expected value one way or the other. So who can explain to me what's going on with these two values here? We have some sort of function of the random variable here, right? I guess I'm trying to hint at something here. Yeah. X squared has the same sign, second derivative as log. What do you mean by that? really need this coffee. Right, we said there was some relationship between these two when I was applying log to x, right? When I applied the log on the inside, it sort of like, um, yeah, there was some relationship between the two, right? One of them was smaller than the other one based on the concavity here. So here we have a concave function, which is x squared. It's concave, well, I guess they call it convex, right? I call it like concave up, but yeah, I guess the proper terminology is convex. So yeah, x squared is convex, which means that the expected value of x squared by Jensen's inequality is always larger than the expected value of x, and then we square it afterwards. And that's just because, you know, x squared is this, has this concave up shape. Oh, this marker is also trash. There we go. Yeah, so because of this concavity feature here, because the averages always lie above the curve, right? The lines, the secant lines for the exponential and the x squared always lie above, like this is above the curve. So that tells you when you're taking the expected values of x squared, it's gonna it's curving those values up, so it pulls this expected value up higher than if you just look at the expected value of x and just square it. Yeah, so second derivative positive, yeah, that means it's convex. So x squared, the second derivative is always non-negative, right? It's only, I guess. Oh yeah, sorry, it's always well, at 0. Yeah, second derivative is always positive. Yeah, sorry, I was looking at the first derivative. Second derivative is constant, right? It's just 2, so it's always positive. It has constant second derivative. And so this thing's concave up, so this expected value is always larger than this thing squared. This is actually an equivalent formula. These two are equal to each other, and that's how we know this is always positive, right? Because this is always larger than this, so that means this is always greater than or equal to 0. But also, I mean, here you can see it's always positive because we're always adding positive values, right? So just another way to look at things. When you do e to the x, you're adding a bunch of terms. Oh yeah. Let's prove it if we want. Yeah. So maybe that's I did want to go over that. Let's just prove this equality here for the variance. I think it's pretty simple to prove. And I believe this is in that first resource that I included on Discord. It's I think you have to go to chapter 6 though to find a variance. So, oh wait, sorry. Yeah, so here's the definition of variance. Right, it's this weighted sum. I'll just use mu for the expected value. And it's just this weighted sum weighted by the probabilities of each event happening. Right, so then what do? We can square this, we can FOIL this out, right? Oops. So what does this become? This becomes x of I squared minus 2 x of I mu plus mu squared all times p of I. Yeah, I was just checking that the formula makes sense. Okay, so yeah, so we're just proving that that second equality that I had written, the separate formula for the variance. So this is just the definition at the top. Now we FOILed out this square here. So we get x of I squared minus 2x of I mu plus mu squared times all weighted by p of I. That's just, yeah, so just FOIL this out. Then, what do we want to do here? Well, I see, obviously, what was the other formula I had written there? Oh, right. Yeah. So xi squared times pi, that's the expected value of x squared. So let's split this. So x of I squared, p of I. This thing is that is expected value of x squared. So what else is left? So we have plus mu squared. So what else do we need? We want this to be minus, yeah, minus mu squared. Oh, right. The sum of the pi's add up to 1. P of i's add up to 1. So I think that's the key. Cancellation. Yeah, right, Jeff. Yeah, so the key here is that when I sum up the p of i's, that's just going to sum up to 1, and we're actually going to need that in this, what ends up happening here. So we have minus 2 xi mu, and then, so none of these, oh, right. And then when we sum up, when we take the weighted average of the xi's, that's just mu. So this becomes minus 2 mu times mu, which is mu squared, plus mu squared, times, well, okay, I'm doing this a little too fast. Let's go a little slower. So minus some 2 xi mu p of I plus mu squared sum p of I. Right. Pull out mu. Yeah. Right. Yeah, we can pull out the mu. Okay, yeah, and then this first part, this is just the expected value of x squared. This, well, we can pull out the 2 also. Let me pull that out also. So minus 2 mu. When we add up the xi's times pi's, that's just the expected value of x, right? So this is minus 2 mu times mu again, plus mu squared, and then when we add up all the pi's, we just get 1, because that's the definition of a probability mass function. All of the probability, all of the weights have to add up to 1 for a probability measure, right? Right, so then, yeah, just rewriting everything. This is expected value of x squared, minus 2 mu squared plus mu squared times 1. So this is expected value of x squared minus expected value of x quantity squared, which is just mu squared. Okay. So that basically, that proves this formula. So the variance, this is the definition, but we can also write it as a difference of 2 expected value. Well, an expected value of the variable squared and then the square of the expected value. out Mew. Stooky. um, yes, Dr. Cold. Yeah, we just decided we're gonna do a 24-hour stream on Saturday. I believe 5 p.m. it'll start. I'll do a little bit of research stuff, so first 2 hours will be probably not for a giant audience, but yeah, the rest of the 24 or 22 hours, we'll just be answering questions like this. Any type of exercises anyone can, hit me with, anything the chat wants to go over with, or wants to go over. Okay, yeah, so where were we? So this first part is expected value of x squared, and yeah, simplify here, we get the formula. Any questions? So this is just kind of outlining two of our main ways to study random distributions, right? We can look at what's the arithmetic average we would expect in the long run. That's the expected value. And we can also look at how wide we expect our values to vary from one sample to the next. And that's this idea of variance, and that's some sort of notion of how far we are away from the mean, right? It's not the average distance, it's actually the average of the squared distances from the mean. So a little bit care needs to be had, that you don't just because you could think this is just, you could take absolute values here, right? And take the average of the absolute difference, but that would give you some other value. I think they call that the spread. I think I was reading in the resource they had a problem about it, but yeah, that doesn't usually come up. This is the main measure that we use for talking about how wide a distribution can vary between values. And also the key here is that if you take two independent random variables with certain variances and you add them together, then the distribution of the sum, the variance will add. So basically we like variances because the variances usually add together for independent stuff with finite, it has to be finite mean, finite variance, of course. But we're dealing with all finite sets here, so everything is finite. That's the beauty of finite sets. We don't need to do any infinite convergence. Let's see, what's the chat saying? Yeah, yes, it is real. Thank you, Dr. Gold. Okay, so yeah, let's move on here. So I think this is a very interesting problem I took from that resource. I keep saying that resource. I think I forget the author, but I think it's just titled Introduction to Probability. I should probably remember the author's name. Yeah, maybe if someone from chat wants to put the author and the resource, the first resource from the probability resources from the Discord, if they want to put the author's name here for everyone. But this is page 247 in that resource. And this is the section talking about expected values, and this is number 6. So we can also do number 7. I actually didn't fully do it out. I kind of got lazy and didn't finish it. So either we're going to do it together or we're both going to be stumped, because I was a little bit stumped, but I didn't really try that hard. So we'll try on number 7. But I didn't really write it out, so it's possible we'll struggle with it, or at least I will. So problem 6, another nice one with the variance is expected value of variance of x given y plus the variance of the expected value of x given y. Isn't that just the same thing twice? What am I missing? Oh, maybe you meant y given x. Okay, so yeah, let's work on number 6 here on page 247. So this problem says we roll 2 dice. X is the sum of the 2 dice. And Y is the difference of those same 2 dice. So the question is asking us, show that the expected value of the product of the 2 variables, x and y, is equal to the product of the expected values. So and I guess technically I didn't write down the definition for the expected value of a joint distribution, or where there's like 2 variables. Well, actually, I guess it's, yeah, I mean, it's still finite. Yeah, technically we have all the information we need. Yeah. So we want to show that expected value of x times y is the product of the expected values. So expected value of x times y is the expected value of x times the expected value of y. Hopefully you can read that. Right, and then it asks, so are these 2 independent? Which I guess I didn't really give you a definition for independent, but we'll just be a little hand wavy about it. We'll kind of give an intuitive notion of what it means. So if x and y are independent, it just means that if I figure out what the value that y took is, it doesn't give me any information about what x is. So it doesn't change the probabilities of x. So basically the probability of x, given I know what y is just the probability of x, and y has nothing to do with the probability of x. Wait, isn't isn't expected value of x times y equal to 0? Yeah, I think it is. Yeah, they're both equal to 0. No, y is just the difference, not the expected value. Yeah, so if you get, oh, I see what you're saying. Yeah, it needs to be the difference in order. So one die is designated D1, the other die is designated D2, and then we're always taking D1 minus D2. It's not the absolute value. Otherwise, I don't think it's true. You know, then I'm pretty sure it's not true. Yeah, so that's kind of the idea. Jeff's sort of getting at the idea here. We can view these as like, let me get my red here. So we can view the 2 dice as like D1 and D2, like a pair of rolls. And x is going to be D1 plus D2, where here it actually doesn't matter the order, but if we take the difference, the order actually does matter. So we need to do D1 minus D2, I think. I guess it doesn't really matter. I mean, you could do D2 minus D1, but you just have to pick one or the other. Otherwise, I don't think the problem is correct. I'm not sure. Well, I only did it this way. Is it still correct if you take the absolute value? Probably not, I would assume. Actually, yeah, I didn't do it with the absolute value. Is it still true with the absolute value? That's a good point. I did not actually think of that at all. So yeah, I did it this way. D1 plus D2, D1 minus D2. And it is true for that. I mean, I sort of expected it to be this because, you know, I saw like a difference of squares thing going on, but maybe I just made that up in my head. From follows whether you want to be an open VC or a private invite only Right. Yeah, I can do guest. I mean, the only thing I'm The only thing I'm limited by basically is I just need to figure out how to do everything. That's the technological aspect of getting it all set up. That's really the only thing holding me back. But that's kind of why I want to do the 24-hour stream too, because that will give me more time to interact with you guys, and you guys can give me ideas of stuff to do, and I'll have just more time to be sitting down and actually setting it all up. So yeah. So what do we think about this? Should this be d1 minus d2 in absolute value? Or should it just be d1 minus d2? Because I think I solved it this way, and I'm not sure if it's still true the other way. Well, no, I could take there might be like a hour nap, 2-hour nap here and there, maybe at like 2 in the morning when no one's, if it's slow or something. I might slip a nap in or something. But yeah, I think the 24-hour stream will get some attention maybe. We'll see. At least hopefully a couple followers. Yeah, that's the thing with the time too, is like everybody's on different time zones. So it could be 2 in the morning for me, but it might be, 12 in the afternoon in India or something, right? Or 4 in the afternoon in Japan, right? So yeah, I'm still thinking about this problem. Well, I'll solve it the first way. I'll solve it the way that I did it, and if anybody out there wants to try to solve it with the absolute value, or if they want to give me a counterexample to show or just explain why it's not true with the absolute value, I think that would be interesting for the audience as well. So yeah, let's work this out. Let me get a new marker. A lot of these are dying. All right, so pretty simple problem. We just need to figure out what they actually mean by this. But we're just rolling 2 dice. X is the sum of them. Excuse me. Y is the difference, and then we're just not sure if this should be the difference in absolute value or not. Do we agree expected value of y is 0? Well, yeah, if it's the difference, then it should be, but if it's the absolute value, then it's not, right? That's the, yeah. Yeah, so in the case that I'm doing right now, yeah, you're correct, yeah. So, so what is x times y? That's the question, right? So if x, this is a brand new marker? No? Thought it was brand new. Yeah, it was brand new. There's no way. Wow. I got ripped off. I swear I didn't use that marker at all. See? Oh my god, everything is not working. Oh, sort of works. So if x is, or let's just write down. So x is the sum. Oh, God. I'm switching to blue. Hopefully this works. Alright, sorry. So x is the sum of the two. Wow, these are just not working. Y is the difference. So what is the random variable x times y? Well, it's difference of squares. Oops. Right, and if we take the expected value of this yeah, so what happens if we take the expected value of this? Well, it's the expected value of d1 squared plus the expected value of, well, minus the expected value of d2 squared. Right? But because these are just independent dice rolls, they have the same expected value, and their square also has the same expected value, so it's just 0. Because, you know, any value minus itself is 0. There's nothing different about the first die and the second die. Yeah, you could think of it as symmetry. There's nothing different about the two dice, and they're not dependent on each other, right? So they should have the expected value, and no matter what the first one is, it doesn't change the expected value of the second one. So these should just cancel to give 0. Right, and then so now we just need to show that the product of the expected values is 0, but by the same argument, the expected value of y is also 0. So yeah, Jeff is correct here. So this part implies that expected value of y is 0. And then we're basically done because the left-hand side is 0 and the right-hand side is something times 0. So it doesn't matter that this is non-zero. This is, what's the expected value of the sum here? Can anybody tell me what that is? That example was boring. Which example? Sum is 7, yeah. Yeah, so the expected value of x is 7, but then times 0 is still 0. So that should be that problem. Let me try one more marker before we go on. The example you're doing now is boring. It's too simple. Well, I'm just picking examples from the book. I mean, I'm trying to go over simple enough stuff so that, you know, people have just, you know, some people are just seeing this stuff, right? We just wrote down the definitions. So something we're using here, though, it's not very obvious. I mean, we are using some properties here. So I'm using the fact that the expected value is additive here, right? Because this was a difference of two things, so we had to be able to split it. So it is simple, but it's not, I wouldn't say it's a trivial problem. Where they're not both 0. Sorry, we didn't finish the problem though. So the last part says, are x and y independent variables, right? That's the, yeah, exactly, yeah, you just, same exact time. So yeah, what's the answer to that question? Are x and y independent? And if so, why? And if not, also why? I think not. So, okay, you think they're not independent, so why are they not independent? Yeah, that was the example I was thinking of as well. Yeah, if x is 12, then we already know what the two dice are. They have to both be 6. So that means the difference is automatically 0. And so, yeah, if x is 12, it determines what y is. So, yeah, it definitely changes the probabilities by knowing what x is. So, yeah, knowing that x is 12 completely changes the probabilities of what y could be. In fact, y cannot be anything other than 0. So, yeah, that shows that they're not independent. Okay, so basically the point of the problem was to show that. So remember in logic, when we go the other way, the statement was if the variables are independent, then the expected value of the product, it does multiply. So then this is actually just expected value of x times expected value of y, but we need independence for that. So this example shows that the converse is not necessarily true. So just because this expected value is equal to the product of the two doesn't necessarily mean that they're independent, and this is a counterexample of that. So you're saying the problem is very simple, but actually I think the whole point of the problem is it points out a very important counterexample to a statement that you think could possibly be true because the converse is true. But this shows that the original statement, the converse, is not true. Yeah. It shows that x and y are uncorrelated. No, here they're like completely correlated, right? X and y almost like some of the values actually of x determine y, so they're like very correlated. Not completely, they're not 100% correlated because only certain values of x determine y, but yeah, I think the correlation is pretty high for these if you did it out. Yeah. Fair enough. If the product of all moments were equal to moment of all products, would it be true? Wow. If the product of all the moments were equal to the moment of all the products, I'd have to think about that one. That's probably above my pay grade, honestly. Yeah, I see what you're asking. That's a good question. Yeah, there's definitely questions about like when do the moments determine the probability distribution, right? So it's definitely a fair question to ask, but I'm not sure the answer, to be honest. I'd have to think about it probably for a long time. Let's see. Anything else? Okay. Let's go to number 7. So this is the one. So maybe this will satisfy you, Jeff. This one's a little bit. Well, I mean, this one's not even that complicated, but it's complicated enough where I wasn't exactly sure of where the argument should go at a certain point. So maybe you guys will help me out for that. So yeah, this is number 7. Okay, so show that if x and y are random variables, taking only 2 values. So x and y are random variables. Taking only 2 values. And if that product from before is true. So if the expected value of x times y is equal to the expected value of x times expected value of y, then they are independent. Okay. So hopefully you guys, can you guys read that, the problem? So show that if x and y are random variables, taking only 2 values. So basically, there's some probability that x takes value 1 and some probability that x takes the other value. And then there's also some probability that y takes the first value and some probability that y takes some other value. Or I guess, so yeah, this one's also a little ambiguous because do they mean that both can only take the same 2 values or can they take 2 different values for each? I think they meant just 2 values total. Like x can take these 2 values and then y can only take these exact same 2 values. But I think the wording in the problem was a little unclear. So again, that's my interpretation of it. I think that's I think that's the only one that makes sense, but we showed that they are not independent. What I just gave you is a definition. Oh, right. Yeah, uncorrelated and independent are different. Yeah. That would have to be dealt with separately. So what's going on here? What's the random variables that take only two values are boring, though not as boring as random variables taking only one value. Yeah, I guess this one's a little less boring though, because now we have two variables taking those two values, and they can vary with which probability each one is taking each, so slightly more complicated. I'm not challenging you there. I'm agreeing with you. Yeah. Okay, so yeah, so what are these two values? We can just call them like A and B. We'll just say those are the two values that they can take. Right. So let's see how to, I'll let you guys think about this maybe for a second while I find a new marker. No more blacks. Yeah, I don't know what happened to that marker. This green one will work. Guys are having math bona fides competitions here. No, I know it was. You okay? Yeah, that was directed at USC. Yeah. Guys, we don't need to flex our degrees here. We're all plenty enough smart. You guys don't need to prove it to me. I was just planning the usual 1 hour today, but depending on how long it takes to get through these problems, it might take a little bit longer. But okay, so let's try this new marker. Hopefully it works. So we're trying to work on this problem. We're trying to show like a partial converse to the last problem, where if they're only allowed to take two values and this product is equal to this expected value, then they actually are independent in this special case. So like we said, there's two values. Let's just call them A and B. So by definition, the expected value of x times y, well, if we only have two values for x and y, then the product can only take three possible values. It can either be a squared, which is the first value. So if x and y are both a, then it's a squared times the probability that x is equal to a and y is equal to a. Or it can be a times b, where it's the probability that x is equal to a, or the probability and that y is equal to b, plus the probability that x is equal to b and y is equal to a. Or they can just both be b, of course. So x equal to b, y equal to b. And the p, the bold p, just means the probability. So I was using like a regular p before, but you can think of it as the same thing, just the probability. I'm right by commutativity. What do you mean? Oh, 4 cases. Right. Yeah. There's 4 cases, but in these 2 cases, the product is both A, B. So there's actually only 3 possible. There's 4 possible outcomes, but in 2 of the outcomes, we get the same product, which is A times B. Right. So what is the other side of the equation? So we had expected value of x times expected value of y. So this is like the left-hand side, we'll say. And then over here, make us some room for the right-hand side. I know I'm messing with everyone's, or maybe I'm dyslexic. This is the left, this is the right. No, but left-hand side of that original equation, which was just this expected value of the product. Right-hand side was expected value of x times expected value of y. And for this stuff here, that just means that it's a times the probability that x equals a. And y can be anything, right? So a times probability x is equal to a plus b times the probability that x is equal to b. And then we're going to multiply this whole thing by same thing, but probability of y equal to a plus b probability of y equal to b. Okay. I guess I'm just writing too big here, but you can kind of see what's going on. There's going to be some sort of foiling going on, right? Because we have this a plus b product over here with the x's, and then a plus b product over here with the y's. And yeah, so this is going to foil. We're going to get like a squared p of x equals a times p of y equals a. And yeah, we'll have a b squared term, and we'll have two ab terms. So it looks very similar to the right-hand side here, where we have one a squared term, two ab terms, and then one b squared term. And we're trying to show that these two are equal. So the part in my, when I was doing it earlier, this problem, the issue I was having was if we are trying to show that these are equal to each other, or sorry, if we assume that these are equal to each other, I don't necessarily see how that implies that, like, we're trying to show that the probability of x equals a and y equals a is just equal to the probability of x equaling a times the probability of y equaling a, because that will show that they're independent. Or maybe we can use that to show that they're independent. No, we're trying to show independence. Yeah, we're assuming that the products are equal. So we're assuming that this left-hand side is equal to this right-hand side. And now we want to show that x and y are independent. Yeah, Venn diagrams is 4 boxes. It might be easier if you assign value to the 4 probabilities. I mean, it should be about the same. I mean, it's just algebra, right? I mean, we could plug in something for a like 1 and something for b like 2, but I mean, it's not really going to change much. Actually, I think it's a little more clear if we just leave it a and b. Right, so let's rewrite this, but essentially we're assuming that this left-hand side equals this right-hand side here. This is equal to this. Let me rewrite this a little bit smaller. And then we'll try to analyze it to try to figure out why x and y are independent. All right, so we have a squared probability that x is equal to a, y is equal to a, ab times probability of x equal to a, y equal to b, plus probability of x equal to b, y equal to a, plus b squared, probability x equal to b, y equal to b, is equal to, and then I'll FOIL this stuff out now, so it's a squared probability x equal to a times probability of y equal to a plus ab times, and now there's going to be two terms, so there's just probability of x equal to a times probability of y equal to b plus probability of x equal to b times probability of y equal to a, quantity all times ab, plus finally b squared times probability of x equal to b times probability of y equal to b. Okay. Whew. Okay, so we're assuming this is true. Here's the equal sign is right here if you lost it. Okay, so this plus this plus this equals this plus this plus this. Oh, we got rated. Nice. Thank you, Zach. I totally missed that. Sorry, I was working on this problem. Oh, no questions. Okay, so yeah, I'm putting it to you guys. Where do we go from here? That's the question here. So if we assume these two are equal, we want to show independence. I forget, maybe Zach, you probably know this. Is independence equivalent to the joint product just being the product of the two? Like if we show that P of x equaling A and y equaling B is just the product of x equaling A times the probability of y equaling B, is that if and only independence, or do we need to show it by the definition? Like that, so something is independent if, probability of x equaling A given y is just the probability of x equaling A. So Jeff says we know that the probability of x equaling A is the probability, oh, good point, okay. Yeah. Probability of x equaling A is just the probability of x equaling A and y equaling A plus the probability of x equaling A and then y equaling B. Very, very, very good point. Yeah, I think that's probably the step I was missing. Yeah, that seems to make sense. Does that give us what we want, though? So we're trying to show independence. So you're saying you want me to split... What are we actually... what's the equation we want to prove, or that we want to use to demonstrate independence, though? I think that's what I'm a little confused about. Yeah, that's the definition, Zach, yeah. Right, sorry, I know you just got here. Let's see. I think if we can just show that, draw a box with two choices for x, two choices for y. Right, okay, yeah, that probably makes it simpler, yeah. You make a good point. Yeah, so let's just look at the actual distribution, right? So there's 4 possible things that can happen, right? So we have, maybe I want to use a different marker probably. So we have 2 things that can happen for each variable. So we have x equal to A, x equal to B, y equal to A, y equal to B. And these all have some probability, right? I guess in general it's just P1, P2, P3, P4. But I don't think I don't think you can just pick any P1, P2, P3, P4, obviously. Or maybe, is it just always true that they're in? No, I think we need this property here. Okay, but what is this going to tell us? Yeah, I mean, so yeah, these are just some probabilities. We know that like P1 plus P2 is 1. P3 plus P4 is 1. Still not seeing how we get the independence here. Oh, sorry, yeah. Wait, so which ones add up to 1 then? P1 and P3? Yeah, P1 plus P2 is the probability that y equals A. Okay, right. Right. Okay, yeah, good point. Yeah, so P3 plus P4 is the probability that y equals B. P1 plus P3 is the probability that x equals A. Oh, right, sorry. They all add up to 1. Right, I'm sorry. Right. My bad. So P1 plus P2 plus P3 plus P4 is 1. And like we were saying, P1 plus P2 adds up to the probability that y equals A. P1 plus P3 is the probability that x equals A. Yeah, right. So we're not trying to prove that these are equal, though. We're assuming that this is true. Okay. Oh, I see what you're saying. We're just, but use the definition. Right. Okay. I see what you're saying. Yeah, Rex, you can mod Zach for sure. Yep, no problem. Okay, but then when is this equation going to come into play, though? That's what I'm like a little confused about. Because obviously we have to use this equation somehow, or else we're just saying that any two variables that take on two values are independent, but I don't think that's necessarily true, right? We'll see, Jeff. We'll see. I mean, so yeah, I'm still not seeing the full argument here. We're assuming that these two things are equal. We know that there's some setup like this where the probabilities add to 1, and we know that the probabilities, if we just forget about y, we can figure out what's the probability of x by adding 2 rows or 2 columns to figure out these individual probabilities, irregardless of x and y. What am I missing here? Yeah, we can write it all using P1 through P4, sure. Yeah, maybe that'll help us a little bit. Okay, yeah, let's try to rewrite our equation using these p's. Maybe that'll make it easier to look at least. So we're assuming that a squared, so our values for our two random variables, they can only take two values, a and b. Assume a squared, so If x is a and y is a, that's with probability p1. AB times P2 plus P3 B squared times P4, and that's equal to A squared, so it was probability of P1, probability of x equaling A and y equaling A, or times probability of y equaling A. So x equaling A is P1 plus P3. And probability of y equaling A is P1 plus P2. It's going to be plus AB. What am I doing here? I'm trying to do it from memory. Sorry. Let me look at my notes. So AB, yeah, P of X, so X being A. Oh, right. So P of X is A times P of Y being B. I feel like it's almost more complicated with the, because now these are just sums. So yeah, X equaling A is P1 plus P3. And then also we want probability of Y being B, P3 plus P4. Plus P2, P4 times Y equal to A, P1 plus P2. So this is multiplication at the end here. Plus B squared times probability of that A is, so P1 plus P3. Oh, no, sorry, P2 plus P4. Times probability that Y is B, P3 plus P4. Okay. Not sure if this helps us, but okay, so what does this get us now? And we know that the sums add up to 1. That's the only thing we know. So we have this equality. We know that the sums add up to 1. And that's it. And then what do we want to show? We want to show that the probability of x given y is just the probability of x. Yeah. Yeah, this one's a little stumping me pretty good. I don't know. I guess we can move on from it in a couple minutes if it's... We could always tackle it next week. I know Stuckey sent in a problem in the Wednesday submission one. I didn't really get enough time to really look at it long enough, so I figure we'll go over it next Wednesday. And we could also finish this one next Wednesday as well if we can't get like a fully satisfactory answer here. Right. Let's see. Okay, I'm willing to move on from this one for now. But I'm sure there's probably some way to interpret this in this 4 grid where this is like much simpler or something. I feel like there's something here I'm missing a little bit. Some conceptual thing, but yeah, I knew this one was a little difficult. All right, well, we'll come back to this one, I guess. So that was 7. I think this means p of x given y equals a equals p of x. Right, yeah, that's a good point. Well, that's what we're trying to show, right? I think that would be equivalent to independence in this case, right? Yeah. Yeah, so we want to show that the probability of x given that y equals a is the same as the probability of x given that y equals b. So probability that of x, y equals probability of x. Yeah, so what does that mean in terms of the PIs, Jeff? How can we reinterpret what you just said in terms of the PIs? Because then maybe that, in addition to this equality, or maybe with this equality we can deduce that statement you're making about the PIs. Yeah, that means that P1 plus P2 equals P3 plus P4, I think. Okay. That would make sense if the numbers are correct. Yeah, so P1 plus P2. So that's the probability of y equaling A. Oh, no, that's just saying that the probability of y equaling A equals the probability of y equaling B. So that would just mean they're 50-50. So I'm not sure if that's the correct statement there. Yeah, I'm not going to give up on this one, though. I think we can just probably solve it next week, which is not a problem. I mean, I think thinking about the problem longer can be beneficial. Also, I don't want to just throw up some, half-ass answer without doing a little bit more due diligence. Yeah, I call him to the stand as well, Zach. Yeah, Zach, can we get an answer to this problem? I mean, I can solve it next week, but if we don't have a nice answer by next week, I think I'll have to do it out on the board. But okay, so let's move on from here. We'll try to figure this one out next week. Okay, yeah, this one was kind of cool. I liked this next problem I picked. So 267, same resource. All right, yeah, we'll put this one on hold officially. Tricky problem though. So this is page 267 in the next section. So this is talking about variance. Problem 21. So let x be a random variable. With expected value mu, which is finite, of course. Well, I keep thinking we're doing infinite stuff, but it has to be finite. So it is mu, and variance is, of course, also finite, which is sigma squared. Problem is show that this function f of x, which is a sum, basically like this weighted sum, but instead of having the mean here, it's xi minus x, little x, squared times p of I. And we want to show that this function has a minimum at x equals mu. And so we're actually combining calculus here into our probability, right? Now we have a function. It's actually a polynomial in x, and I believe it's actually just a degree 2 polynomial, right? So it's just really a parabola. And we want to show that the minimum of the parabola is at x equals mu. Okay. So how do we use calculus to solve this? Or is there a way to avoid calculus here? I used calculus, so I don't know. I'm curious if anybody has any other solution. So we're just taking basically like the squared the probability weighted squared differences between some number x and the values that the random variable takes on with. So each value in the state space is I, and when the state space is in state space I, the random variable takes on value x of I. So this is just kind of like a weighted difference, or it's like a weighted average of the squared differences between the values that the random variable can take and whatever this number that we're plugging into f is. And so we want to show that this is minimized when x is mu. Differentiate each term and set the sum to 0. Yes. Yeah, so why does that work? So from calculus, I don't think I got this far in the calculus lessons I was doing, but for optimization problems, right, we want to find when the minimum is, we want to find when the derivative is 0 usually, right? So we're going to take the derivative of f and try to set it equal to 0 and solve for this point, and hopefully this point will be what we want to show it is. Oh, maybe you can do this without calculus. Yeah, so how do we do this without calculus? I guess I'm using calculus, but I'm really just using power rule. Well, I guess I am using calculus, yeah. What's the way to not use calculus? How would you show this without calculus? When I see an optimization problem, I almost automatically think calculus. I'm not sure how you would even think about it. Well, I don't think it will have a maximum, right? Because we can always pick any number x that's like really, really far away from any of the xi's, and that will just get larger and larger, right? So this grows without bound. There's definitely no maximum. It's like a parabola. Actually, I believe it is just a parabola, right? Because we're just adding a bunch of x squareds. Yeah. X minus x equals x minus mu plus mu minus x. Okay. Does that give us what we want, though? You can do this without calculus. Oh, I see what you're saying. Does that work? X. I think I see what you're saying. X minus mu plus mu minus x squared. What does that tell us, though? Okay, well, let's just do the calculus way. I'll check back with you guys if you have another way to do it, but I think the easiest way to think about it, at least, if you know your calculus and power rule, is just this is a sum of degree 2 polynomials. If we take the derivative, we can just do it term-wise, so we can use the power rule on each one. We can pull the 2 out and then take the derivative of the inside, which is -1. So, yeah, let me make a little bit more room, but essentially we're just going to take this derivative, set it equal to 0, and try to solve for x and show that there's only one solution, that x is mu. Okay. Maybe I'll leave up f of x here. Okay, so f prime, let's just leave this right here. F prime of x, like I said, we're going to take the derivative termwise, so we're going to pull out a 2 and then a -1, so we're going to get a -2 here times x of I minus x, and then the 2 becomes a 1 by the power rule, and p of I is just some constant, well, indexed by I. Right, so this is just I in the state space. Right, and if we set this equal to 0, then, yeah, now we just want to solve for x here. Okay, I'll look at that in a second, Zone Ranger. But, so, yeah, just focusing on this way. So we have this equal to 0. I can move all the x's to one side, or all the x. I guess it is more than one, right? Yeah. So this implies that, yeah, just move all the x times pi's to this side. So this is equal to that. So -2 times sum I x of I times p of I is equal to x times sum of the pi's. And again, we're using the property that all the pi's add up to 1. So x is just equal to, oh wait, I need the -2 here. Yeah, there should be a -2 here. Right? Yeah. Right, but the -2's just cancel, so I think we can just ignore those. So this is just saying that x is the sum of the xi times pi, and this is just the mean. Right, so x is mu. That's what we wanted to show. Your eyes hurt? Why? Because of the... Yeah, I'm sorry about that. Okay, so just to summarize, we have f of x is this sort of like variance-like equation, but instead of a mu here, we have an x, and we want to show that it's minimized when x equals mu. We took the derivative, used the power rule, separated this stuff to the other side, cancel the -2's, and then this adds up to 1, so we just get x is equal to this, which is the mean. Okay, so that was an interesting one. Any questions about that? So what was Zone Ranger? I don't want to spend too much time on it, but I would like to understand what you're saying here. So, see, f of x is the variance. Oh, okay, I see. Are you sure you can do that? I feel like you can't do that for some reason, but I'm not exactly sure why. I feel like it's not linear, right? Because you're with the squared in there, so I feel like you can't split it like that. It seems like you're trying to make like x squared a linear function. But maybe I'm yeah, but then you can't split that square, right? Like x minus mu plus mu minus x squared is not equal to x minus mu squared plus mu minus x squared. Like squaring is not a linear function. But that's okay. That's, you know, common mistake, right? Think everything's linear. That's fine. No, I might be thinking of something wrong. I'm trying to interpret your you get a cross term, it is not a mistake. Yeah, maybe it's not a mistake. I can't really do the math in my head right here. It's possible you're correct, but okay. What else? Did I miss anything else here? Yeah, calculus works. I mean, I have no problem with calculus, especially for polynomials. Just because like the derivative of a polynomial is another polynomial, so there's like no real issue with that. No, I believe he is trying to say something. I don't really have the ability to check it right here in my head. A is x minus mu, b is mu minus x, a plus b squared, right. Okay. Then take the expected value of both sides. Okay. I want to say yes, but I don't. I still think I would need to think about it a little bit longer. Okay, just because we're going a little bit over on the time here. I had one other problem here, but I don't see any reason why we have to do it today. Are there any other problems we wanted to work on right now? So that was 21. I have 29 here, which is a problem about a Poisson distributed variable, and then they ask to prove the mean and prove the variance are both lambda. I don't think it's trivial though, so I'm probably not gonna do it out right now. It might take 20-30 minutes. Oh, okay, so pen is on. Yeah, let's probably just raid somebody right now. 24-hour stream, yeah, just for anybody that's listening. That will be on Saturday. In my time zone, it's 5 p.m. starting. I'll do a little bit of the research type stream like I did last time, and then we'll just keep going for as long as we can. Bring as many questions as you can possibly handle. I might try to set up some sort of like call-in type thing where we can, you could just like call in and ask a math question, and we can try to work on it on the board. Assuming all the technology questions can be solved, but I'm sure it's not very hard. I can probably just have people call up in Discord or something, and I'll figure out how to connect the audio with that. So yeah, Saturday, 5 p.m. Eastern, United States time. I'll get my snacks. I'll get the coffee. Probably have a couple coffees or Red Bulls going. Maybe take a nap at like 2 or 3 in the morning, and then do more math in the morning. Let's see. Any questions I'm missing here? I don't know. I was curious. I think it was wrong. Do you know calculus of variations? No, calculus of variations. Yeah, that's something I don't know very much about. So yeah, I would like to know more. I mean, I know the term. I've looked it up, I'm sure, at some point, but I'm not really sure what it's used for. I wouldn't even be able to tell you what it is off the top of my head, other than I've heard of it. 24-hour math. Yes. My brain will definitely explode. I'll probably need to take a 24-hour nap after, but okay. Let's send it over to Pen Center if he's streaming. Yes, prepare to defeat me, please. Yes. Try your hardest. Okay, let's raid Pen Center. Let's send it over.